Okay, thank you very much. It's my pleasure to join the symposium. It's of course a bit difficult because the people that are in this building see my presentation every 2 weeks. So now the challenge is how to be entertaining still. So I thought that I show some of the projects, but maybe from a different perspective, from the perspective also of the symposium about playing models. I entitled the talk "Building Undrawable." This is an early study where I analyzed Christopher Alexander's pattern. What's the name again? Pattern language, and because I'm interested in how we can support or which kind of instruments we can use in the design process that go. We were first at the previous talks a bit talking about bias, and I'm looking forward to overcome my own bias by using these instruments that help us designing, help us to be more creative, maybe exceed our own, the capacity of my own imagination and being surprised and stimulated by the computer or by the digital. And also the title refers a bit to an older lecture series I did together with my colleague Michael Hansmeyer back 2010. It was also already entitled Undrawable. Here we focus only on the computational design aspect, not on the realization. And then back to my background, I'm related also to Ludger Hovestad's group. That was one of my first student works I did together with Ludger Hovestad as a professor about the models of computer games, the levels and how we perceive them as a kind of architecture. So that is closes somehow the circle. Yeah. So I will talk now about the way which kind of processes we use for modeling architecture, for designing architecture, breeding, growing, finding, learning models, but also about how to materialize them. So it's a very important aspect of our work, how we bring our designs back to reality, how we can manifest it, but also how we can play with the process of the materialization. And one first project uses an evolutionary strategy, so it's about breeding architecture. It's an early work where we basically just studied, can we let the computer compose the circularity of a building by an evolutionary process, by creating many, many variations, and we give some target constraints that we want to fulfill, and we let the computer fold this architecture that maybe reminds us a bit about some Colas concepts of a continuous space. But what is interesting for us as designers then is that we can basically just work with the process without a preconception of the space in mind, and then later explore what is the proposed solution. And so that means we take a different perspective towards the design than if we would have drawn here every single triangle by hand. And here some of these studies. We didn't manage yet to materialize those structures. But it's a circulation where you don't cross the path, where you don't need stairs, but you can explore manifold variations. So these kind of evolutionary processes we use quite often also in projects like where it's about housing, where we let the computer just create as free as possible variations, and we basically not control the outcome of the design, but rather the properties. We filter out the properties that we would like to achieve. The growing aspect, so that's more about maybe not about finding optimal solutions, but more about refining geometry, refining form. And here an important work was always done together with Michael Hansmeyer about subdivision processes in the computer, where we basically inverse the process of smoothing geometry based on a limited set of control points to increase the surface of geometry by a parametric subdivision process. So you see here a two-dimensional diagram of this process where we would split lines, split and fold the geometry over and over based on a set of parameters. In 2D, that could be comparable to, or 3D, that could be comparable to folding of a paper. And what we control then with the computer is the folding ratios in order to articulate very specific geometric forms. So the input shape of this form is a cube, and it's subdivided over and over. I mean, our subdivision processes are almost integrated in every CAD software, but we don't use it for smoothing, but for rather articulating the shape. And what is an important aspect here is the way we control these subdivision processes. So we have a kind of a data mining between the iterations. So these are millions of triangles that we then classify into different regions according to properties. So we create very specific zones. You cannot do this manually anymore, so we have to do this by basically categorizing them in different fields, and then we apply different subdivision rules in different regions. So that allows us to exaggerate some of the initial properties of the geometry, further articulate them. And it turns out that this kind of process of reacting on already procedural generated geometry and further informing the next procedures based on the distribution of properties of this procedure allows us to replicate existing styles, but also create new ones, like in these studies of domes, where we then breed an entire family of domes based on just variations of these subdivision schemes. Yeah, and maybe a project that we didn't show so often here, that was our contribution to the MoMA PS1 competition, Phenomena, which uses a similar process. So we are then also interested in really constrained outer boundaries and create this inner fountain, grotto-like shape already. That should be the background for the PS1 festival. We didn't won, obviously. At this time, I think the water infiltration system won as a for the. But you see here geometry that is basically not, none of these geometries is drawn. I mean, none of the geometries that I show in the talk is drawn, but all derived through these procedural methods. In this case, there's no optimization, just aesthetic optimization. So we would breed a set of variations and then filter out the ones that actually inspire us and come closer to our original intention. How to materialize then these projects? A very early study was another model. That's a Modellstadt, again, a city model, a Stadtigel that was created at Ludger Hovestad's chair together with Alex Lehnerer. That was for the Urban Biennale in Rotterdam. So that's one of our first 3D printed models, actually. And how to scale this up, we took inspiration of a work from Mario Botta, which is a basically layered a replica of a Baroque church, San Carlino, that was temporarily constructed at the lake in Ticino. And our previous colleagues, Tom Pawlowski, developed a 3D printer based on this principle that can use cardboard. So it's a one-to-one 3D printer that cuts and glues cardboard layers together. You see here his study, so that's not my design, his study of stools that can be then excavated out of this low-cost but very fast 3D printer. And we use this then to actually build this Stadtigel in 2010 out of thousands of layers of corrugated recycled cardboard. So it's still, I think, one of the most sustainable 3D printing methods. We don't know where this sphere actually ended up. It was suddenly lost at the Biennale, and maybe it's rolling around somewhere in Rotterdam. But so, of course, Michael Hansmeyer's work was also based on this principle. Here in the building, laser-cut cardboard layers, these columns that he did, and just I show it because it's another variation of the theme of constructing in layers. We continued also to investigating the topics of columns, but asking us how can we materialize those in different ways. This is a study together with the MIS 2016 with our postgraduate program. The challenge of this one was just that it was the smallest columns we ever built. So we work with a photoresin printer. So the forest of columns you saw before was just would fit on a stamp. So that was also the smallest exhibition we could ever do. We continued working with this idea of a forest of columns, also with an entry to the Architecture Biennale Venice. So today I show all the non-winning entries we did together, Michael and me. Here, not being mature enough with the 3D printing methods, we designed the columns based on the principle of milling them out of a massive block of foam in this case. Here just some visualizations of how we imagined this forest of columns in the Deutschen Pavilion. space-defining columns. That's a topic that you probably see also in many of the projects that I'm showing today. And these are also grown, of course, with a similar subdivision process. There was another aspect to this project where these columns would not be static columns, but they would be placed on autonomous vehicles. And so these constellation of columns that we would find in the German pavilion would permanently change. So the columns would interact with the visitors and then form maybe classical configurations or free configurations, and therefore very much changing the appearance of the space. Again, not one, maybe we try it again. That's why we have a little robotic platform over there to test this. So the concept was called Wandelhalle. So just that in this case it would not be the monks that walk around the columns, but the columns walking around the visitors. And then we became more mature with this 3D printer that I show in every talk. What is fascinating is the resolution that this 3D printer can do, the 40,000 by 60,000 pixels per layer. So we were talking before about pixels. Here we have a machine that can help us to inform a material on a very small scale in a very fast time. There was the next column we did for the Architecture Museum in Basel, woven column. So only the column is printed. And assembled here. Also, in this case, some parts are missing, actually. We have one sample over there, but the other two parts somehow went lost. But the idea is here maybe to play around with the topic of weaving a bit, and also, of course, finding geometries that are, in this case, maybe not undrawable, but maybe also very difficult to fabricate out of stone in with different techniques. And then finally, the digital grotesque projects, where the aspect of growing geometry became very important. We did many studies, usually running the computer overnight, and then on the other morning looking at the different variations that it would create out of these 20 or up to 100 sets of parameters that we can finally control in this subdivision process. And these are just some iterations of the design we developed. And it was always the search between chaos and order, between something that is a bit familiar, so not too random, not too chaotic, still relating to some architecture vocabulary, but still also seeking for surprising moments. So that was really an interaction with the computer in the sense, or with this procedure, that we would come in the morning and being surprised what was calculated, and then learning from these results and recalibrating the process. In order to come up with designs that we would not have imagined before. And then the level of scale is important, and also working with physical models. So that is another 3D print in 1:10 that we did back then. But it turned out also that this process of also having a physical output in between still is very important. And it turned out that printing this, you see it over there, the physical model, was at this time also faster than plotting the entire space. We did a one-to-one poster plan here of a grotto design, but printing this one monolithic 1-to-3 model of the grotto also could be done in a single day. So that's an exciting development, that the materialization of the objects becomes also so directly connected to the design instruments. Just some surface studies. The idea and the search was about how to code these structures. At the beginning, being very optimistic that should be real gold. We are now maybe checking how can robots do that, but back then it turned out that it's far too expensive. Not in terms of material, but in terms of work. Next scale was then using fake gold, but still manual work. And then at the end, this prototype was sprayed in fake gold. So different iterations of surface treatment. Different questions about materiality maybe as well. But for us, it's also important to have the right material in order to have this interplay of shadow, the sensatoric experience that we can provoke with these structures. On the technical level, different digital representations of these geometries become very important. This is a self-intersecting cut of one of these subdivided shapes. So nothing is controlled beforehand. All the manufacturing constraints come afterwards in order to have the maximum degree of freedom of the design. So we developed our own methods to clean up this is a cleaned up section now of one of these grottos. We worked here with now voxel-based models, so the pixels that we were talking already before turned into 3D pixels, and at the end the resolution of this is, I think, roughly 3000 by 3000 by 1000 voxels, such a volumetric model that helps us to construct actually at the end the shape, to define the most important aspect of such geometry, the aspect what is inside and outside. But also all the connection details are calculated on the voxel level. I skip a bit the technical part, and also here the illustration of the fabrication you have seen probably already. Assembly here, dry joint connection. So we were pretty precise, and just some illustrations of a test assembly in Switzerland, in Zurich, at Schlieren at the construction hall. So that was an interesting experience, because also of the delay caused by the huge amount of data, that made it very important to figure out strategies how we can play with these models. Because that means, okay, you have to wait for a day until you can see what you are generating, etc. An important aspect of the work. Maybe just to show how we further develop these methods, because what we found out in this project is that actually our geometric resolution was the limitation. So the printer could deliver more details, but we could not generate more details. So we refined the algorithms that we use to control the geometry. This is the follow-up project Arabesque Wall, where you can see maybe also these different representations, different models that become important into the design aspect. Light simulation, so rendering, but very important, and then finally the materialization. And for us, the little artifacts that you see, depending on the manufacturing process you use, are also an interesting and important part of the entire process. In the second iteration of the grotto, now we work with geometry that is not only folded out of paper, but also cut and glued together. So that means we can work with more complex topologies, more like sponge-like structures. As you can see here, multiple degrees of depth on the surface and many layers. Here just the visualization that this colorization scheme happens based on these classification principles that I talked before. So we paint these structures based on what kind of properties the individual millions of facets have. And here, studies of Grotto 2. Grotto 2 is basically an aggregation of many different of these schemes together composed in one project. So these are just the segments studies. Yeah. So it's a curiosity also of form. It's a curiosity also how these different kinds of orders come together, also how they can be materialized, and what architecture we can compose out of these structures. This is now a movie from a printed object of the Grotto 2, which maybe also shows the translation now from the rendering that you've seen before to now the physical artifact. Again, I skipped the technical details. Just here some documentations of the installation at the Centre Pompidou. Computer crashed, I think. It happened before, so we have maybe a little break. Unless you want to sit in front of this image for the next hour. No, but I think I have to really reboot the tab. Huh? No. I think I have to reboot. Okay. Too many triangles, yeah. No, but I think it's... image of Grotto 2 now. I skipped some slides, but you see maybe that really there's different orders and on different scales of magnitude here, but also in different locations. Now, maybe quickly a work that was also not authored by us, but by Christian Geritz, and so we took over the digital fabrication part, but I thought it's maybe interesting to see here, or maybe seek for some parallel aspects in the design process. So that's the incidental space Venice Biennale pavilion contribution from Christian Geritz, and he worked together with students, I think, building almost random physical models out of gypsum casting and being in the role of just selecting actually the best fitting design to his intention. So it's a very analog process, but I think there's some similarities in terms of how you derive forms. So that these are photos from these gypsum models, renderings. This is the space itself as a negative volume that we had to fabricate. We developed here again a method that allows us to automatically generate formwork system for these shapes. Here the structure. And for us, this project was also interesting because it's basically also questions a bit the typical categories that we would use when we are talking about architecture. It's maybe also seeks for, okay, what are the limits of architecture a bit? And working with these geometries, it became interesting that one would classify these parts of the topography that we see here by almost same naming principles that we use when we are talking about mountains. So there are some specific valleys here, or some regions with very refined geometry, some with a rough texture, but everything derived from a physical model. At the end, built in a very performative, actually 20mm concrete shell with the help of Josef Schwarz, and here some photos of the final installation. So this 3D printed formwork, we continue working with this process. It allows us to mediate between the digital manufacturing process and conventional materials, or a wide range of materials. In this case, it's a shape memory alloy reinforced staircase that will be opened next this summer. And we use also machine learning to basically augment the design process. I guess you're all familiar with these topology optimization principles that help us to reduce materials and components. And in this case, we developed a surrogate model approach where the machine learning can predict how an optimized structure would look like depending on playfully placed obstacles in the structure. So in that case, you learn as an input, the obstacles, you simulate the result. This takes a long time, but then you have a real-time interaction with the computer. And I think this kind of real-time interaction between the digital model, between the design intention, allows you to really start playing in a different way. So it's a categorical difference. It's not just making it faster, but it allows really to design and play with aspects that probably would be difficult beforehand. And here, a model, and we use this also on different scales, but I think this would go now beyond the talk. Maybe to the physical aspect, the geometry that I showed before was mostly driven, the forms are mostly driven by geometric processes, and we are also interested in discovering new geometries by physical processes. So in this case, it's a printing process that actually is not calibrated well. I think Anna over there, leading the concrete printing research, can tell us more about this. But even those can be considered as failures. We are also interested in what kind of geometry, what kind of form is derived from these processes. We discover new patterns, for example. I mean, at this moment, we are always aware that we have to clean the printer again and again, and this takes a long time. The challenge of 3D printing, as you know, maybe with concrete, is that you have to have the right timing between gaining strength and still being soft enough to bond between the layers. So the process is now calibrated, but the question is maybe what to do with these kind of, you see also here an interesting model in the background that is supposed to be a flat element. But so how can we also maybe make use of these kind of structures? So in the Tor Alba project, a project that we are currently building, we try to make use of these, we call it material-driven ornamentations. So I skip a bit the background. It's if you still have time, it's worth a visit, a Swiss mountain village where the tower will be placed here. Many people are involved, as we heard in the previous talk, so I just have not time to go in detail about all the peoples that are involved here. The final design, the way it is built now, is a composition out of columns. What else? I mean, after hearing my previous projects, we play a little bit with the typology of columns. In the base, it's massive, very volumetric columns, so darker spaces, and you ascend the tower and you come up in a space that is provides an overview to the entire village here. We do fabricate these columns in-house, so they are all printed now already. There's a reinforcement integration, but what I wanted to talk about is rather the level of ornament that we here now not control entirely and directly by geometry, but also by the process of materialization itself. So it's a different category, less control again, but for us also working with similar topics of, okay, how can we introduce different scales of geometry into architecture? And how can we also be surprised about some of the results? Maybe I skip here this video, but just to illustrate the entire project. So that is the Moulins village. There's currently 16 inhabitants in this village. 8 of them are in favor of the tower, and 8 maybe not so much, but I think once it's installed, it will be different. Our client is a cultural institution, the Origin Foundation, very generous and also very much involved into the planning process itself. The foundation seeks for unique spaces that allows them to have a counterpart to typical performance scenography in order to stimulate creative processes between the artists and the stage, which is the tower to a certain degree. It's also a stage for the events there. You see the growing of these models here, the growing of the tower, and the topic of the branching column that is that we play with from level to level, introducing also asymmetries and a higher degree of branching. So every single column is printed, and this is the assembly hall, and 2 levels are already assembled now from the tower. This is the lowest level. It's already more than 3.5 meter high. You see there's cast parts, 3D printed parts, and cast parts again. And here just further studies of the ornamentation. That's all the lowest level, so the smallest. The highest level is 6 meter high columns plus a 5 meter high cupola. So other materials we are working with, maybe to wrap up. So we are interested in working with different materials in a single printing process. So in this case, it's a reinforcement printing of carbon fibers. That's a work from Yunchul Kwon here, to create these kind of furnitures. He also integrated SMA, so another dimension into 3D printing, the dimension of time and movement. That is an SMA smart material, so shape memory alloy that is integrated into 3D printed structures and their movement can be controlled by the 3D printed structure itself, as you can see here in these images. We add also additional dimensions by working with different plastic extrusion principles, so not scaling them just up massively, but also working with hollow filaments in the 3D printing process that allows us to increase the structural, optical, and thermal performance of plastic printing, but also adds another aesthetic dimension to the models. And you see here the 3D printing process in action. And what it allows us to do is now, there's Matthias Leschok and Nick working on this process, is to control, for example, the amount of air that we blow into the structure, and therefore adding an additional dimension to the printing process itself. Here's some studies done together with the students. Here you see it very well, that there's some larger inflation and some lower inflation, and all this resulting in quite interesting physical properties of the artifact. Again, a mix between robotic control, geometric control, and material-driven control. I wanted to end with a work from Vasily. He works on ice formwork, that's his research topic, And here, this relationship between the material process and the form definition is, I think, very visible, and resulting in also shapes that we would not be possible to maybe design otherwise and fabricate otherwise. The process is quite poetic because it relies on melting the ice in the same speed as the concrete is curing. So that means a very soft demolding and capacity to create these very interesting porous structures. Here some student works. I mean, Vasilis here, you can ask him later. You can also maybe visit the freezing container where these objects are created. It's one of these structures here. So I would say no very predefined geometric control, but a lot of freedom given to the material process. Huh? And that allows to also then control these different degrees of porosity. Yeah, and so I wanted to end here with this. I think we are living in an exciting time because I think we are in a time of convergence between the instruments we are working with, the instruments and how they are manufactured. That's a GPU close-up. The instruments we can use for materializing our designs and designing our designs, all this coming together through the digital, and that allows us to further play. Thank you.
Thanks a lot, Benjamin. Maybe just one question. When is it opening, the tower?
Difficult to say. End of September, hopefully, but there's no official date yet.
Do you have to convince a lot of neighbors to approve that?
No, that's already approved. Yeah. So.
Questions?
Benjamin, thank you for the presentation. I enjoyed throughout the whole presentation how consistent this idea of geometry and detailing has been throughout your work. And one question, not question, but rather word was coming all the time to my mind, and this is the idea of craftsmanship. And I think this could be interesting to talk in relationship to your work, because we're always thinking about the grotesque or the Gothic as these very intricate, handmade, long process things. And your early work and your latest work is really trying to still have this level of detail, but the long process is being taken over a particular construction system. And then for me also, it will be really nice for you. It will be very nice if you could also elaborate into the mass production of things. Like, what if you see a balance between craftsmanship, the detailing, and mass production?
The microphone works. Yeah. Well, that's of course really an interesting question, and also a question that we are permanently confronted with and asking ourselves. I think so. The original idea is not to romanticize craftsmanship, so we also really conceive our work as not trying to redo craftsmanship, but there's a related aspect. So I think the aspects that good craftsmanship can add to architectural design and architectural space, this is the aspects that we also relate on this work. So working in different scales, working with also variations, and basically also adding an extra effort to the work. And I think that's an important point. So when we're talking about this relationship between mass production and the projects that I've shown, I think that's still a lot of work that we have to put in. But that's also an important aspect, because that means that the value of the spaces we are creating is higher. So it's a lot of intellectual effort. There's a lot of designing behind it. The process is, of course, rationalized to a certain degree, but it's not. You could build easier a tower of this height. So it's about a certain adding values to architecture by appreciating also what we do or what we construct here as an artifact. But then there's of course also rational aspects that could be in other projects become very important and also industry relevant, on really the other level of making architecture more affordable or etc. But the specific projects I've shown here, I think they rather maybe celebrate the extra value we can put into the architecture. So at the moment where I think we would now work with methods that are at the end completely effortless, then probably would look also at a different perspective on these projects. So I think the effort is important.
Maybe I can ask a question. So, big fan. I'm completely in love with all of the projects that you've shown for a very long time. And I'm curious because you never talk about it, but the aesthetics, the quite consistent aesthetics that are present throughout the trajectory of these columns, and now the Storia Alba as well, is Geiger-esque. Neo-Gothic, I don't know. I don't want to pin it down, but I'm wondering, how do you reflect upon that? What, do you like it being called Gothic or Geiger-esque, or
I think people refer often to Geiger or Giger, the Swiss artist that was responsible for the Alien design, but that was not really a reference. But of course, there's maybe some similarities also in the alien-esque, like because we are seeking for a bit of a different language, but as maybe very well visible in the digital grotesque, that it still relates to an architectural order, but creates an alternative version maybe of it, and that might relate also to the alien aspect of Giger in his works. But so it was not a direct intentional reference. And the idea of these works is that people can interpret it and read it in different ways. So that to be able to interpret these architectures in different ways and read them is an important aspect of the design. Also. So we are happy if not everyone reference Giger.
It was a beautiful presentation and so inspiring seeing all of these different iterations in place on these geometries. As you also just now mentioned this idea of architectural language and this like searching for new architectural language, I was so incredibly curious when you were saying in these subdivision processes you developed kind of names for certain regions, and then later on you spoke of how like in the other project you were almost referring to it as like geological features. So because this is like one speaks of architectural language in terms of geometry, but like this is a case where like an architectural language is actually at work when you and your colleague are going to decide what kind of part of that kind of ridge behaves to that rule or to that rule. So I was just super curious, what are the kind of terms that you came up with to describe these features?
I mean, that's really depending on the project, and I think we also learn of how other people. Now we are working in the tower project. There's many people involved in the construction, and they give also names to some aspects. So maybe to give just one example, but that's also not the most beautiful. But so the base level of the tower has also no real name. So first of all, there was a debate if this is level 0 or level 1, because it's actually a non-existing level floor. And then it also has no direct architecture reference. So people would call it a Flaschenhals in German, a bottleneck. It becomes this now currently the terminology that is used for this part. That was not the intention also. But it became very important because now people know what we are talking about, which part of the tower. And yeah, but so in the other project that was designed by or found by Christian Keretz, there it was basically then the many different names. It's a whole cartography. I should make a diagram of those.
It's really fascinating.
Thank you very much for your presentation. I am just a little bit curious about if you would have to choose a specific material for making this kind of designs. I know that each material has its specific properties and each design has its specific requirements, but which material do you think is the most reliable for, in general, to use or with this kind of techniques?
Also a good question, and I think a constant search, because I think now including also Michael, who does a much more project also with this, the range goes from styrofoam to marble, huh? And so I think very interesting materials are materials that come with a certain inner life already, as maybe a marble stone, where you have an additional level of surprise and you have an additional layer in your design, the inscribed texture. But we did also projects where we created we printed artificial marble and made an algorithmically generated marble texture that would spatially go through a synthetic material. So I don't have a direct answer, but I think ideally it's a material that can also surprise us in these systems. Yeah.
All right. Thank you very much, Benjamin.
Thank you.